Thank you. So now, I will try to be faster now because and explain a very nice work that has been done by one of my former PhD students, Lisa Bloom-Moise. Lisa has defended her PhD 2 months ago, and she will start a postdoc now in Constance in Germany. But she did all what I will show you now. So the question is about up-down cortical dynamics. So I don't know if you know what is this. Those dynamics, they are population dynamics in cortical neurons that you very often see when you do electrophysiology with anesthetized animals. And what happens is that you enter the neurons enter a regime where they alternate spontaneously between periods where they collectively fire quite much for 0.5 to 1 second, and then everybody shuts up, and you have a period of silence, and there again autonomously you have a new up phase, so alternance between up and down phase. This is a real experiment that you can find here in the somatosensory cortex. Each line is a neuron that has been measured with an electrode and spike sorted, and each point it's a raster plot, so each point is a spike, right? So you see this alternance between up and down, and if you compute the mean firing rate of the network, you have something around 4 to 5 hertz for each up phase. And if you look at what happens in the down phase, really you have almost no firing. It's not like you have sometimes one spike there, but it's almost completely silent between both. And the duration is something like around 0.25 seconds for the down phase and around 1 second for the up phase in the other red. But it's a large distribution, and it's also observed during in awake animals or even during tasks. So it's not only in anesthesia that you see that. So the question, of course, is how can you explain this kind of collective phenomena? It's like how do you call that in stadium, the ola, you know, when everybody gets up and puts his hand. When you do that we see that in Europe at least. I don't know if you see that there. So collective dynamics are up, everybody chats and everybody sets down as well. And the first experiment that were important is that experiment where people took the cortex of the animals, and it's a bit difficult, like they severed the external input. So they removed all the input to the cortex. Most of them comes from the thalamus, for instance, and they could cut that. And what they observed that even if you cut the external inputs, they still have this up-down oscillations. So it's an intrinsic mechanism. Somewhere there has to be an intrinsic mechanism that does that. And so you can find a very large set of computational papers that try to explain this intrinsic mechanism. And most of the time, what you have is an activity-dependent mechanism. The mechanism says that if in the past a neuron has fired a huge amount of spikes, if it's been very active in the past, you will have a mechanism that make them less active afterwards. So some kind of activity-dependent feedback with some delay. So this could be slow adaptation current, short-term plasticity, whatever. But the idea is always the same, that if you've been very active, you tend to be less active afterwards. But it's not all, because in fact, afterwards, experimentally, people have found that even if it's intrinsic, still, if you have the oscillatory inputs that you get from the thalamus in the cortex, still have a strong impact. So people have used the model to try to understand this interplay between these intrinsic rhythms and the intrinsic mechanism that makes the up and down dynamics. And very recently, of course, I wouldn't talk about that if it weren't about astrocytes. 2 papers by Chiara Poscanzer and Raphael Yuste have shown that astrocytes are very important for this, to the control of this up-down state. So what they did, first it was in ex vivo, so in slices, So they double patched one astrocyte and one neuron that is not far away from the astrocyte, and they just stimulated the astrocyte. So they stimulated it with electrical currents so that it becomes active. So they see its huge amount of calcium in the astrocyte when they stimulate it. And then they record during the stimulation phase whether how many up phase they find and how many down phase they find in the astrocyte, in the neurons. And what they found is that, so this is the gray, the control phase, and the pink zones are the times where they stimulate the astrocyte. And you see that if you look at the up phase, that the straight lines there, the up phase, they are most of the time always in the phase, in the pink phase, that the phase where the astrocyte has been active, has been simulated, and they are almost much more less likely to appear in the control phase when you don't stimulate the astrocyte. That's what you can see here. Then, so if you look at the number of up states where everybody talks per trial, it's much more likely you have much more up phase statistically when you stimulate the astrocyte than in control when you don't stimulate it, but the amplitude and the duration are almost the same. So somehow, when you activate astrocyte, you have more up states. So that's exactly what you wanted to model, right? How can we explain this control of the up and down state by the astrocytes? And for that, we will use spiking networks and explore the dynamics with a bifurcation analysis. Okay, so the first thing we did, so we started with a model that is a bit specific model. It's a network of leaky integrate and fire neurons. I don't know if you're familiar with the term of leaky integrate and fire. It's a very simple model that you have here. It's a model where you have the voltage of a neuron that it decreases exponentially, except that it gets recurrent input from the other neurons, and external input from some external noise, right? And when in the model, so the voltage fluctuates and it can increase because of the input. And if it goes above a threshold, which is the firing threshold, that is a parameter that you set, then you say that the neuron emits a spike, and you reset the potential to 0 or to the resting potential, and then it can go on, right? So it's a very simple model where you integrate the input. If you get higher, your voltage gets larger than the threshold, you emit a spike and you go on. And what do you do with the spike? But this spike will be transmitted to the neuron that you are connected with, and through a synapse, it will increase the current of the synapse. Okay, and this, in this case, it's this paper by Alex Roxin and his colleagues. What they did, so they have a population of excitatory neurons, a population of inhibitory neurons, and what they added, the two components that met the up and down phases. First, they added an adaptation current. I will come back to that. This adaptation current gives you the up and down, and this is adaptation is very simple. That this current, this adaptive current, when you have a spike that is emitted by a colleague that is connected to you, right? It will increase the value of I, and the value of I will have negative amplitude impact on V of the associated of neuron is connected to. So it will decrease it. So it will remove it far from the threshold. So it will make so that it will hyperpolarize it in a way, right? So it's a way to control the fact that if you've been very active, you will have many spikes. If you have many spikes, this I will be very large. If I is very large, V will decrease and it will get very far from the threshold and you don't fire. But that's an interesting mechanism. Anyway, and then what they did, because they were theoretical physicists, and they had a very special synapse that is a single synapse for all the population. So that's a very weird model where, if you want, all the excitatory neurons, they have a single synapse that they contribute to, and all the inhibitory neurons, they have also a single synapse that they contribute to. And why did they do that? They did that because in terms of calculation, in terms of mathematics, it's much easier to analyze afterwards. Okay. So that was the model. And we know that with this model, well, you have, so again, excitatory and inhibitory neurons with external input. This can explain, this can have up and down behavior. So we took this and we just said, okay, now how can we add the astrocyte in the game? Well, as I said before, maybe since we don't know exactly what they did, the astrocyte, what they do, maybe we can somehow modify a neuron model. Again, so as I said before, it turns out that if you look at the input-output relation of the astrocytes, when the input increases, so you have more glutamate that comes from the neurons, you have more calcium. And if the calcium is larger than the threshold, you will release glutamate from the astrocyte. And the shape of this release is very similar, or is a bit similar to an action potential in a way. So there are differences. Of course, the timescales are very different, right? If you look at the spike, the electric spike in a neuron lasts like some milliseconds. The glutamate spike in an astrocyte lasts like some seconds. It's very different. The typical frequency is different, hertz versus 100 times less. And the integration time is very different. Also, the time it takes for two signals to be integrated in the astrocytes, it's milliseconds versus seconds. So what we will do, we will use models for astrocytes that are also integrate and fire, except that we will change the time scale. We will adapt the time scale so that they correspond to astrocytes and not neurons. And there you are. That's what we have. So we have the three equations that you had before, and then we had astrocyte there. And this is not the voltage for the astrocyte. This is the release of glutamate. That is how glutamate is released, right? And it's also a leaky integrate and fire, meaning that this quantity G varies. This is related to one astrocyte. And when G becomes larger than the threshold, then the astrocyte emits a glutamate spike, and the glutamate spike will be added to the neurons as well, right? Again, the difference is that compared to neurons, the time scales for the astrocytes compared to the inhibitory or excitatory neurons are much larger, and the delays are much larger as well. So it's an ugly model, I will say, because it hasn't been done for astrocytes specifically. It has been done for neurons. It's a leaky integrate and fire, but it's a very easy way to do it. And the connectivity now. So I don't want to go into too much detail, but again, it's a model where you have no single synapse, and we keep this idea with the astrocytes. So we have astrocytes and so on. We have 50%, half of the synapse are tripartite. I told you that in vivo it's between 30 and 90%, so it's something not so bad. And that's what we will do. So now, first, what we did, we run simulations, right? Numerical simulation of the stuff. So what I show you is the case where we have no astrocytes. So you see here the voltage of one excitatory neuron in red, one inhibitory neuron, and you see the voltage is very small. At the beginning of the simulation, you have some spikes there. So some of the excitatory neurons release these spikes, some of the inhibitory neurons as well. But after the first spikes, you have nothing. So everybody is in the down phase, right? There's no up-down phase with those parameters. Everybody is in the down phase. Now, you take the same parameter, the same numbers, and you add astrocytes, and then all of a sudden, you see the activity goes in. And in fact, you see again, if you do like the raster plot, so again, each line is a cell, neurons, inhibitory neuron in blue, excitatory neuron in red, and glutamate release events by the astrocyte in green. And you see alternation of up phase and down phase appearing that are very clear there and there and there. You can see them at the level of individual neurons as well. You have upstate alternating with downstates, upstate, downstates, and so on. If you look at the average spiking rate, it's there for the excitatory neurons. Is on average, it's around 5 Hertz, which is what they measured, roughly. So it works. But something very strange is that if you look at the green points, so that's the astrocytes, and they seem that they are not oscillating. They seem that they are, everybody gets up and down, the excitatory and the inhibitory, up, down, but the gliotransmission, the astrocytes, they seem to be delivering glutamate at the same frequency. And that's very weird. In fact, when we started to have this kind of stimulation results, at first I thought that it was a bug in the program, because in any dynamical system, if you have a dynamical system with 3 equations that are coupled, if 2 variables oscillate, the third will oscillate as well. It's not possible to have, if they are connected and if they are coupled, you cannot have 3 stuff oscillating and 1 connected variable that doesn't oscillate. But we'll see, we will understand afterwards why is it like this with bifurcation diagrams. But at least we have a model with the astrocyte that is very similar to what is observed experimentally. We can even compare the duration of the up and down state and the variability. This was experimentally measured. So the mean duration of the upstate is 0.65 seconds for a CV of 0.61. In the model, we have a bit more for the mean duration, but the CV is the same. And for the downstate, the numbers are similar as well. So this convinces us that we have a model that behaves a bit like what is observed experimentally. So now we'll try to understand how come, what is the impact of the astrocyte on this, and how come that the astrocyte allow this up and down phase. And the first thing we said is we thought is that, well, all this looks a bit like noise, right? The input of the astrocyte. So maybe the astrocytes are just a source, another source of noise, because the external input is a random stochastic input, so it's noise. Maybe the astrocytes, they just add up to the external noise inputs. So what we did, we came back to the model without astrocytes, but we increased the noisy input, the external noise, twofold, right? And indeed, what you observe that somehow we can have, in this case, when we, without astrocyte, but with more external noise, external input, we can have some kind of alternation between up and down phases. The difference is that between, if you compare that and to experimental data, in the down phases there, where you still have the down phases, they are not completely silent. You still have many spikes there, whereas there in down phasing, you almost have no spikes. And that's different, but you can do it. The other difference is that if you compare there, so that's the voltage of one excitatory neuron taken at random, and this is an inhibitory one. You see that you don't see the up and down phase that you saw before. If you look at what we had before with the astrocytes, that's here. In a single trace there, you see really clearly upstate, downstate, upstate for the voltage there. And we don't see it, we could just increase the noise. So how can we explain all this? These are simulation results. We run simulation of that. How can we explain that? The only way to explain that is, of course, to do a bit of mathematics, and that's what we did. And we get back to what has been done by physicists more than 20 years ago. That's a mean field analysis, and it's not that complicated, but it's a theoretical analysis that starts that. But in our case, it assumes that all the cells receive an identical input that is random, but it's a Gaussian input with independent and uncorrelated external input. Uncorrelated means that the input of two neurons are not correlated with each other. In this case, in fact, you can assume that the incoming synaptic input are just like diffusion. So it's a diffusion term, like what you have if you had Brownian noise as input. And in this case, you can compute the membrane potential and its distribution, the probability that the membrane potential has some value x, and this is given by a Fokker-Planck equation typically, and that's the equation you have here. So you have the variation with time of the distribution p of the potential Vx with time, and it evolves with a diffusion. This is a diffusion term that is related to the oscillation of the variability of the sigma of the variance of the noise, and this term here is related to the mean of the noise of the external signal, right? So if you have that this differential equation with the correct appropriate boundary condition, you can do the same for the synapse here, and then this allow I give you you have the references of the paper there, when you can then compute the stationary solution, so the solution a long time, and is given by this equation. And in this equation, it's a bit nasty, but you have this integral. Still, you can compute it. So what can we do with that? Well, it turns out that if you apply normalization, in fact, P, the stationary distribution is a probability, so the sum must sum to 1. Then you can have an equation that gives you the firing rates for R for the population X, X being E or I or astrocyte or A. And this is given you by a self-consistent equation that you have seen here. That is a bit complicated because you see that you have Rx0 there to the left, but since you have Rx0 as well here, Re0, I0 in the IREC. The IREC in turn they are in the term IE and I and IA, and the term IE and II and IA are there in the Y, and the Y are here, right? So just to explain why it is self-consistent. So that means that this is the equilibrium firing rate of the population. So again, we started with the membrane potential of one neuron or each neuron individually, and we were able to have the fixed points, the equilibrium firing rate for the population. And for the population, so you have Rx0 there and Rx0 there. We cannot find the value analytically. We can find a formula for that, but numerically, we can solve the equation and find Ri0, Ra0, and E0, right? So that gives you the mean firing rate, the fixed point of your equation. Now, fixed points are not enough. You have to find also the stability. So again, the stability, you can find it with a linear stability analysis. So like in every linear stability analysis, you perturbate your system around the fixed points, and what you get, because it's linear stability, you get eigenvalues lambdas that are here, and you get an equation that gives you the eigenvalues. And again, it's a bit complicated. I want to go into too much detail, but the idea there is that you have functions there of the eigenvalues in the equation that give you an opportunity to find numerically, because you cannot do it analytically, but numerically you will find the values of the eigenvalues lambda, and by definition if the real part of lambda is positive, then your stationary point is unstable, and if it's negative, it's stable, right? So now what we could do is this kind of bifurcation analysis. So what you see here is the evolution of each of the fixed points. So the mean average, the average rate of firing for the inhibitory neurons in in blue, for the excitatory neurons in red, and for the astrocyte in green. So the average firing rates when you increase one parameter, which is the amplitude of the noise. So there you have an increasing amount of noise. And what you see with astrocyte, for instance, is that for most of the time, for all this region, you will have three fixed points, right? One fixed point with a large value that is here. So you have a high firing. One fixed point that is there in full line for the small value. low firing rate. And in between, that's the dashed line, you have an unstable fixed point that separates the two. So you have a bistability regime where you can have either a large firing rates or low firing rates. And that's exactly where, of course, you have your up-down transitions. In fact, what you have in gray there is the result of numerical simulation. And that's the zone of the parameter when we see in the simulation the up-down transition. And you see that is exactly the zone when you have this bistability. So you have coexistence between two steady states, again, one with high firing rate and one with low firing rate. And you will go from one to the other depending on the adaptation. And that's what explains what we see, what we have this with astrocytes. Now, what happens if you remove the astrocyte, or if you inhibit the astrocyte, then this is here. This is the same bifurcation diagram, but without astrocyte. Now, what we see is that we still have this bistability regime there, one up, one down, and one in the middle that is unstable. But the stability regime is much smaller, and it goes only for very large noise amplitude. So that explains that you can have without astrocyte, you can have bistability, you can have up-down regimes for large noise because you have to go there. Whereas if you stay here with an average level of noise, then without astrocyte, you only have a down state, so you have not up-down regime. Whereas with astrocyte, you have up and down, so you see the alternation of up and down. So that means that to make a long story short, what this tells that in the game, the astrocytes they don't change much the bifurcation diagram. They don't change the bifurcation. They just change the parameter range for which bistability exists. So it's more likely to have bistability. So it's more likely to have up-down transitions. And there's something that is very interesting for us as well is that if you look here, you see that with astrocytes, you have the distance between the up branch and the down branch here. It's very large for neurons, red and blue, but for astrocytes, it's very small. So the down branch, so the branch of astrocyte that is on down state is very close to the branch for the up state. That means that the astrocyte, when they go from the down to up state, they will have a very small change in their firing rates, right? And it's exactly what we see in the stimulation there, when it was not clear for us why the astrocyte there, they seem to fire in a regular way. In fact, they fire more there than there, but the difference is so small that it's difficult to see. And again, that's what your bifurcation analysis confirmed there. So that's nice. And that explains why you see no clear up-down regime for layer transmission. Okay, now this was for the mass. Now if you say, okay, let's remove this single synapse stuff and do a tripartite synapse that is a real synapse. So now we had one synapse per neuron, so many synapses, and then we have a situation where the calcium from a tripartite synapse is communicated to the whole astrocyte. Okay, I just told you 1 hour ago that it was not true, but still, that's the only type of model that we have. So in this case, if you have individual synapses, you will have to connect them and define where you connect them. And what we started was a kind of small world connectivity, meaning we put the cell in a excitatory, inhibitory, and astrocyte on a single line, right? We connected them to their nearest neighbor. That's what you see, the connectivity matrix there. This is the connectivity between E cell, excitatory cell, and themselves, between E cells and inhibitory cells. And the black point is when you have a connection, the synapse. And what we did, we just connected each synapse to its neighbors. And we did a bit of rewiring, random rewiring. It's not clear that, but we rewired some of the connection to have a small world connectivity. And if you do that, that's what you get in terms of the same simulation as before with astrocyte. It's a bit the same as before. So you have up and down regime and transition. The difference is since you have everybody is not connected to everybody. Your up and down, your up phase, they are a bit clustered, a bit segregated, but you still have an up down. And then, so after that, we go to a different connectivity. We still have small worlds, so everybody is connected to his nearest neighbor, plus some rewiring. But then we add modularity. We add clusters that you see here. That means that you're not connected to all your neighbors, you're connected region by region. So the E cells are connected to themselves and to some neighbors and so on. And in this case, what we were very surprised to find is this type of regime. So this is the type of simulation that we get when we a bit diminish the gliotransmission at the beginning of the simulation. And you see that you see the same regime as before at the beginning. And then sometimes you see a silence there, nothing happens. And after the silence, you see an explosion of activity, and everybody starts to talk, and everybody starts to express firing rates. And this was very interesting for us because maybe this rings a bell for you. In fact, this is very similar what you see in epileptic seizures. This is a recording when you see many recording of like 150 neurons during a
moi je ramasse les gens d'habitude au passage, sinon.
À chaque fois, c'est pendant que je l'ai pas, il y a la multiplier un petit peu.
Ah non, moi je vais à midi. Là, c'est parce que
À chaque fois, mais.
j'ai gardé ce que je l'ai mis, ils n'ont pas fini en fait.
Ah, ils n'ont pas fini.
Pourquoi j'entends plus?
Ils sont ah bah oui, mais en même temps, il y a eu.
J'ai baissé le son. Tu en as parlé? J'ai baissé le son. Non, je crois que c'est sur le zoom. C'est le zoom. En fait.
Ah, tu penses que c'est quelqu'un de...
Ah.
Ah, alors je
Ah, sinon, tu n'as pas poser une question. Mais il n'y a personne qui suit sur le... Non, il n'y a personne.
Non.
Oui, tu peux muter.
J'ai fait le mieux. Voilà.
Merci. Yeah, so if you compare the two raster plots, this is the one that we obtained by the simulation and the one that was measured experimentally for an epileptic seizure. You see that's very similar. So probably maybe we have there something that could be a model for epileptic seizure. And what is nice with this model is that with this case, that usually when you want to simulate an epileptic seizure, you have to change everything around neurons. You have to change the excitatory, inhibitory neurons. You have to remove the GABAergic connectivity, this kind of stuff. Here, we just perturbate the gliotransmission. So we just perturbate the astrocyte. And the perturbation of this astrocyte is enough to generate a seizure that looks pretty much like an epileptic seizure. So maybe that's what's ongoing work, of course. Maybe that's something that we have a model of epileptic seizure that is triggered by astrocytes. Okay, so some take-home messages right now. So what I try to show you that, okay, if we use models for astrocytes that were derived from neurons initially, it's a gross simplification. It's not very nice, but still it allows mean field analysis. So it allows you to do theoretical analysis and bifurcation analysis. And that's important because if you do only numerical simulation, at some point you say, okay, I find this in my numerical simulation, but it is robust. It is really something that is made by my simulation. Isn't it a bug in my code? This happens. And you are never sure that you can explore all this parameter phase, whereas you can do that if you have some kind of mathematical analysis. And that's why it's important to have it. And what we've shown that with this very simple model, the addition of astrocytes, when we add astrocytes, it's enough to put a neural network that is initially silent and to have it alternating between up and down oscillation state, which is exactly what's been reported experimentally. And if we compare, we see that in fact astrocytes, they don't change drastically the bifurcation diagram. They don't change the number, the name of the bifurcation, and so on. They just move the location of the bifurcation and the branches. And this is enough, of course, to change many things. What I didn't show is that what is very important to reproduce experimental results is that the time scale of neural integration between neurons and astrocytes must be very different. Meaning that if you take the same equation that I show you and you put the same time scale for neurons and for astrocytes, we'll never see this kind of up-down oscillations. And then what is also very important, I think, is that we found a dynamical regime where, in fact, the activity of the astrocytes seems to be always the same. The excitatory neurons and inhibitory neurons, they go up, down, but the astrocytes, they seem to be stationary. And we understand why, but this is very important to know that this kind of regime will exist, because if you are an experimentalist, what you will do, you will measure calcium in the astrocyte, you will see that it doesn't change with the up-down phase of the neurons, and you will say, okay, those astrocytes, they are not connected to the neurons, which is not the case. You can have cases where astrocytes are connected to the neurons have huge up and down transition, and these astrocytes still are connected, but they remain at a almost stationary pace all the time. So that's the type of new regime that is useful to have, and that you can have with models, because of course, if experimentalists read this kind of paper, which I'm doubting, but if they read this kind of paper, they can interpret their experimental results differently. Okay, so with that, I thank you for your attention. If you want more detail, all what I've shown you, almost not the end for the epilepsy, but all that I've shown you is published in this PLOS CB paper. And if you have some question, I will be more than happy to take them. Thank you very much.
Okay, thank you very much.